Okay, so let me start then. I will record this lecture and I will put it on YouTube. So good afternoon, everyone. This is Abhimanyu. I am a research scholar at IITD, and this is an extra session, interactive session for this course. So mm since only the contents up to week 9 will be coming in the final exam, so this is just a recap of some of the main concepts of the course. So we will go through some example problems, and while going through these problems, we will refresh the theory part also. So the first one that we will be going through is elimination, and then there is Newton-Raphson. Then we will look at MATLAB functions fsolve and f0. Both of them, especially fsolve, it is a very useful function and it will be used in other areas also. Then we will look at numerical differentiation and integration, and then a few inbuilt functions of MATLAB for these integrations, trapezoid function and the quad function. Furthermore, we will be looking at the Simpson's one-third rule. Then there is ODE solvers of MATLAB. So particularly, we will be looking at two ODE solvers, ODE 45 and ODE 15S. After that, the last part that I want to take is the interpolation and linear regression. So I will be going through the inbuilt MATLAB functions and then some example problems. Okay, so let us start with Gauss elimination. So this is a basic algorithm of Gauss elimination. So suppose you have system of equations as Ax is equal to b. Like suppose let us take this example. So we can convert this into a system of equations as Ax is equal to b, where x is the vector of unknowns. So that would be x1, x2, and x3. Then the A matrix is the matrix of the coefficients, constant coefficients. So which in this case would be 1, 1, 1, 2, 1, 3, 3, 4, -2. And similarly, we will have the vector B, which is the right side of this equation. So 4, 7, 9. Now what we want to do in Gauss elimination is to make this full screen. Yeah, so we have Ax is equal to B. Now we want to create an augmented matrix. Augmented matrix is nothing, just concatenation of these two, uh, like this matrix and this vector in a column-wise manner. So we will be getting a augmented matrix as 1, 1, 1, 2, 1, 3, 3, 4, -2. And then on this side, we will have 4, 7, and 9. Now, what we want to do is for Gauss elimination, the algorithm says that uh, we need to convert this matrix, like this augmented matrix, into upper diagonal form. What do we mean by upper diagonal form? Is that we want a matrix such that so suppose it's a matrix. So all of the terms below the main diagonal, all of those terms are 0, and we have only terms on this part, and then we will have this vector over here. So it is sort of like Ax is equal to b, like if I call, okay, let me use the eraser. Yeah. So suppose this is the matrix, and then we have this x vector. and we have B. So while we are doing this operation, whatever operations we are doing on this side of the matrix, they are also done on this side. So this B is not same as this B. Let me just say prime and this as A bar. So we have this A bar and B bar. Now what we can do is that since this is an upper diagonal matrix and we have only one A and n term over here, non-zero term, others are zero. So we can simply find xn as whatever the bn value is and divided by a nn. So yeah, once we get that, uh, it is like here we will have a n minus 1 comma uh, let us take like m and then a n comma m, like that. So we will get something like if it's a 3 cross 3 matrix, then this would be basically A22 and this would be 2 3. So A22 times x2 plus A32 times x3 is equal to B2. Now we already know x3 and then we can simply do this as x2 is equal to B2 minus A32 x3 divided by A22. And we can continue doing this until we get to the first term of this, like first term of this x vector. So that is basically the Gauss elimination. And so the important part of this Gauss elimination is how do we construct this upper diagonal matrix. So what we usually do is that let me clear this. Yeah. So what we usually do is we take the pivot element. What is pivot element? Pivot element is the diagonal element of this matrix. So like for this first column, this first row, this would be A11. For second one, A12, A22, and then A33. And we take that as pivot element, and we try to make all the other elements of that column zero. So whatever operations we will do on this column, the same will be done on this column. And likewise, we make these two column elements zero for the first row. So we will get something like 1 1, and whatever some terms we will get here, and we will get something here. So what do we do that for the first row? We want this element to be zero. So what we usually do, we take row 2 and we replace that with row 2 minus whatever. So like 2 minus 1, 2 divided by 1, and then we multiply that by row 1. Okay, like this is our coefficient and we multiply that by row 1 and we solve this. Okay, so similarly for the other row. So yeah, the update equation is usually this, basically this. And then once we get the upper diagonal matrix, we do back substitution. Okay, back substitution nothing but just we take this element and we calculate x3 and then we use that x3 to calculate x2 and like that. Yeah, so that is basically Gauss elimination. Yeah, one way we can do this is using the obviously this algorithm, and the other one, the inbuilt MATLAB command is the LU decomposition. So what LU decomposition basically gives you is it converts this A matrix into two matrices out of which one is a lower diagonal matrix and the other one is upper diagonal matrix. Okay, so what happens is that AX is equal to B. That is our equation, right? I can write this A as right. Now basically this ux is basically I can call that as y. So it becomes ly is equal to b. Now yeah, I think it should be. Let us take that as LU only. Then this basically becomes ly is equal to p. So now we can calculate like this is a lower diagonal matrix. What lower diagonal matrix is just yeah. So we can still do this backward substitution, and we can calculate our y vector from here. Now we know that y vector is u times x is equal to y. So now this u is a upper diagonal matrix. So we can again do back substitution and get our x as the redesired solution. Uh, So when we are using this equation, Ly is equal to u, this L is a lower triangle matrix. So that is not actually backward substitution. It's like we are starting from the first element and then we are going downwards. Okay, it's just opposite of back substitution. Uh, yeah, so that is there. In Gauss elimination also we are basically doing this step. We are getting this upper triangular matrix and then we are doing that. Okay, so now we will look at how to do this in MATLAB. Then we will get to the next problem. So I will just share my screen from MATLAB. Yeah, I hope my screen is visible. Yeah, fine. So this is our augmented matrix 1114, 2137, 34, -2, and 9. Okay. I have written this as A, but it's not A, it's basically A along with B. Okay. And now the unknown n is just like how many rows rows are there in the how many columns are there in the matrix, not the columns, basically how many rows are there in the matrix. So this many number of times we need to run the loop. Fine, I'll do this. So we get 3, that is the number of rows. Okay, it's basically a square matrix, so it does not matter if we calculate the column or rows. Fine, so now let us start with Gauss elimination. So first we need to calculate the factor. So the factor would be the like first one is from this loop will go from 1 to, in this case, 1 and 2 2 times. So we need to convert this row and we need to convert this row. And then there is another loop which goes from like, so if I go to this element, then I need to do the operations on this element and this element. So if I go to the second row, then I just need to do this one time more, right? So that is what this inner loop does. Okay. So the outer loop is for the number of number of rows I have, or the number of columns I have, and the inner loop is how many number of rows are there below the row that I'm concerned with. Okay. So for I is equal to 1, this is my pivot element, and so this is the first row that I'm concerned with. So there are 2 rows below this, so this inner loop will run 2 times. Fine. For the second row, I have only 1 row below that, so this inner loop will run only for single time. Yeah, so I calculate this factor and then I just multiply all the elements of that row yeah, with this with this factor times the row above that. Okay. And then this part is the Gauss elimination. So whatever A matrix I get after that, it's a upper diagonal matrix, and then we do the back substitution. So we start with like if I have 3 elements, so the back substitution needs to be run twice. So I start with n minus 1 and I go until 1. Fine. And this is just like I am trying to I take this okay, so let me just run the Gauss elimination first, and then I will. So what should I do? I will add a section break over here, and then I will just run this section. Fine. So this is the A matrix that I'm getting after the Gauss elimination. So now back substitution is basically I am calculating my x n minus 1, which is in this case is like x3. No, so I already calculated x3 over here, and now the rest part is like I am doing for the other part above that. Okay, so x3 is nothing, just my this a n comma n times divided by a n n, and this is for all the other 2 rows. Okay. So here a I end is basically this element, and then a I plus 1 to n, that is this one, this part over here. It just basically means this part. Okay, multiplied by xi. So I will be multiplying it by the element that I have calculated until now. So which in this case would be just x3, and then divided by x22, a22. Sorry. So that will be this one. If we go to the first row, then this is my this part. This will this part. This part will basically multiply these 2 elements of this matrix with x2 and x3, subtract it with a end, and then divide by a11. Okay, so we'll do this. Okay. So yeah, that is the final solution for this. Okay, so I think I have stored it in X. Okay, so now we can just check if the solution is correct or not. So I will just do A is equal to 1 1 1 2 1 3. Oh, sorry, 2 1 3 3 4. Yeah, so that is my A matrix. So if I multiplied that by X, then I should get B, right? Yeah, so that is my B vector 4 7 9. Okay. So now this is Gauss elimination. Now let us try to do this using LU decomposition. Okay, so let me just look at that. Uh, yeah, so this is the code function for LU factorization or LU decomposition. So it returns an upper triangular matrix U and a lower triangular matrix L such that A is equal to L times U. Okay. Yeah, so I think I wrote it. Yeah, wrote it correctly. Fine. So this is our A matrix. Let us do LU decomposition on this. Fine. So we have this L matrix and this U matrix. Note that this is not like it's not unique, right? So I can I can take some elements common now from this side and then multiply that those elements with like I can take some constant out from this side and then multiply that constant with U matrix. So I get a different L and I get a different U, but overall like L times U will always give me A matrix only. So which we can check over here also. So we get our A matrix back. Yeah. Okay. So what I had already told you, like it's like, let me, A is equal to LU, right? So that basically means that LU X is equal to B. Okay. Right. So now let us try to find Y, which in this case, like I am, Y is basically U times X. Okay. So Y would be, I can just directly take L inverse times B. Okay. So let me first calculate B vector. So I can O times X. That is my B. So now my Y is L inverse of L multiplied by B. Okay. So that is my Y vector. And now I will just again do Gauss elimination, or I can in this case take inverse because it's a square matrix. And if I take the determinant of U, yeah, so it's a non-zero determinant, so I can take the inverse. Fine. So that in that case, my X would be, or I will just call this X B, uh, inverse times inverse of L multiplied by uh, yeah, multiplied by Y. Sorry, sorry, inverse of U. Yeah. So this is our XP and this is our X. So we are getting same answer for using both the methods. Okay, fine. So now let me go back again to iPad screen. Fine. So this is Gauss elimination. Similarly, we have Jacobi elimination, and we have Gauss, not Jacobi elimination, Jacobi method, and then we have Gauss-Seidel method. Both of those methods are similar. Yeah. In So the next one is Newton-Raphson. This is also what we are trying to find, basically zero of a function. So it is based on the first order Taylor series approximation. We Fine. So is there any way? Okay, I don't think so. Fine. So in Newton-Raphson, we basically estimate, like, suppose this is our function, y is equal to fx, y is equal to fx. And we are trying to find a solution. So suppose we have this point as our initial guess. So we take the slope of this function at this point. So we get this pink line, right? And then, okay, how shall I begin? Let me just write y is equal to f of x. If we write the Taylor series approximation, uh, do I need that? Actually, I am better without that also. So this is the slope of this function at this point. Then we draw a straight line, and the point where this line cuts the x-axis, let us take that as x2. Okay. Then the equation of this straight line would be f of x1. This is just 0. x1 minus x2. So equation, this point is basically x2 comma 0, and this point is x1 comma f x1. Right? And yeah, so this, and then the slope would be f prime of x1, and yeah, that. Okay, fine. From this I can get that my x2 would be minus plus x1, so I can get, okay, yeah. So f of x1 divided by f of x1 prime is equal to x1 minus x2. So x2 is basically x1 minus of x1 f prime x1. Okay, and yeah, so similarly this is our next point. So at this x point we calculate our fx of y fx2, and then we take slope on that point, and then we get this x3 point. We calculate the function again, and like that we continue doing so until we reach this point, where the, like, if I do this, then I get this, then I get this, then eventually I will get to a point where I will calculate my xn, and then f of xn at that point would be 0. Okay, so that xn would be my root, right? So that is basically what is written over here. To find the formula of x2 in terms of x1, we use the fact that slope of L is fx prime. So the equation is y of y minus fx is equal to fx1 x minus x1, right? And then yeah, we calculate the intercept. Then we find the next point, and we continue doing so until we get convergence. Okay, yeah. So this diagram over here, that is basically the Newton-Raphson method. This I showed you is for a single variable. We can extend this case to multivariable. The only difference for the multivariable case would be, is it here? Okay, it's not here. So let me. Yeah, so for multivariable case, we get this, like, x becomes a vector, this becomes a vector, uh, this also becomes a vector, and this f prime x becomes a matrix called, like, we calculate the Jacobian. Okay, so the update equation basically becomes x prime x minus j inverse of x. Yeah, so if this is like x1, so this is x1, and this j inverse is at x1. Okay. like the Jacobian calculated at x1, fine. So in 3D, I can say I have some sort of 3D surface over here, and then I want to find where this surface intersects the, like this is like x2, x1, and then I have this z or y, matlab the solution. So I have some function like f of x1 comma x2 like that. Okay. So I just want to calculate where this intersects the z is equal to 0 plane. So this is basically I'm trying to do a gradient descent in 3D surface. So some point here, I go from this point to this, like that, and I calculate and I reach a 0 point. Okay. So we'll look at one example of this in MATLAB. So this is the function. So we have three unknowns, x, y, z, and we have three functions. So f1, f2, f3. We calculate this Jacobian. Jacobian is nothing but del of f1 with del x1, del of f1 with del x2, del of f1, x3, f2 with del x1, del of f3 by del x1, del of f3 with del x3, del of f2 with del x3, like that. Okay. So this is basically a differentiation of f function with f1 with respect, partial differentiation of x1 with respect to x1, x2, and x3. In this case, x, y, and z. And this one is partial differentiation of f2 with respect to x, y, and z. And this is f3. Okay. And this is our update equation. Fine. So we will look at this on MATLAB. Close this. I think I had the function somewhere. So graph some multi-variable. And this is the equation. Okay. So this is a Lorentz function. So I have named it Lorentz, but I will change that to our equation. It's the same name. So the first one is x minus y. The next function is 2x minus xz minus y. The third one is xy minus 3z. Okay. Fine. So even though it's written like numbers, but eventually the x variable is whatever the first value of x, this x vector, y is the second, and z is third one. So eventually it will just give me a vector of 3 cross 1 in numbers, like it's a scalar vector. Scalar, yeah, it's like not a scalar vector, it's like a constant vector. And this is my Jacobian. So I take this derivative of the f1 with respect to x. So I get 1. Then with respect to y, I get -1. There is no z in this, so I get 0. This second equation with respect to x, I get there is a 2 over here and then a minus z over here. So I get 2 minus z. Then with respect to y, so I have y over here, so I get a -1. Then with respect to z, so this is like the coefficient remaining would be minus x. Okay. And then the last equation, the first one is with respect to x, so I get a y. The second is with respect to y, so I get an x. Third is with respect to z, so I get a -3. Okay. The function, what it does, it basically takes as input a vector of 3 cross 1 numbers, and then it calculates the function value, f value, and the Jacobian at that given x, the capital X. and it outputs that to this Newton-Raphson method. So yeah, so we just need to give an initial guess, what initial guess we are taking for the function. Then there is tolerances. So when to stop the iteration, right? So what I am doing is I am calculating this absolute. Okay, let me go through. So I will run this loop 50 number of times. It can stop before that also, but the maximum number of iterations would be 50. My x is x0 and x old is x. Okay. Uh, yeah, so I initialize with the same x values, but eventually it will change. So I gave this x0 as input to my this function NR equation. It gives me output the function values and the Jacobian. Then I use my update rule. So yeah, this is my update rule, xi minus ji inverse times f, right? So I calculate the inverse of this Jacobian, multiply it by f, and then I subtract that from x. Okay. Yeah, so I'm basically storing every x. You don't need to do that. Then this colons and everything, they would not be here. I am trying to store everything, so that is why these are being we see these indices over here. Okay, so this will give me output a 3 cross 1 vector. X I is also 3 cross 1 vector. So we do this calculation. We store this as an xi plus 1. Okay. Then I calculate the error. So I calculate the absolute values of the current x value and the old value. So right now x old is just my initial value, but eventually, yeah. So once this error has been calculated, I change my x old to the current x that we have calculated. Then we check for the tolerances. So yeah, this error, it's a 3 cross 1 vector, right? Because this x I plus 1, it's a 3 cross 1 vector, x old is 3 cross 1 vector. The absolute is just, it will just give me the absolute value. So it's still a 3 cross 1 vector. So that is why this tolerance vector over here, it's also 3 cross 1 vector. So we check that all the three values of current, the difference between the current x and the previous x is less than 10 to the power minus 6, and for all the three values, first, second, and third. And if it's like that, then we break out of the for loop and then the problem and the computation. Okay. Yeah. So I think that is it. So I will run this now. Yeah. So the program has run. We can see that the x that it returns us. So it's a yeah, so it's a 1, 2, 3. So the program runs for 5 iterations, and then after 5 iterations, if I check at the error vector. So after okay, let me do format long, then I calculate error. Yeah, so after 5 iterations, I can see that my error has reduced to less than 10 to the power minus 3, minus 6, and so the iteration stops. Yeah, so the x that we got, the final solution that we are getting is and sorry. Yeah, that's the final solution that we are getting. And if I put that in my NR equation, so let's see, the F value that we should get should be 0, right? Mm, yeah, so let me pass that. Yeah, so you can see that the F value that we are getting is 0, right? So that means the 0, 0, 0 is the solution to this problem. Okay, we can also see that if we put 0, 0 over here, so this becomes 0. then 2x minus this also becomes 0, and then xy minus 3z. If I put 0 0 0, then this also becomes 0. Okay, now let us run for some other initial condition. Yeah, so 0 0 0 is a trivial solution to this problem, right? Like 0, it's basically, we can see that there is no constant, so the no constant being added or subtracted. So if we put 0 0 0, then that basically is the solution to this problem. The other solution is if we change the initial condition. So what is happening is so it's like a 3D problem. So I will just explain in 2D what is happening. Right? Suppose we have a solution like this, right? Or this. Yeah. So you can see that we have three solutions over here, right? So suppose I start somewhere over here. So I eventually I reach this point. So that is that is like one solution. But if I choose some another initial guess, suppose I choose my initial guess somewhere over here, like not there, somewhere over here, then I eventually reach this point. Okay. So that is like the other solution. And then eventually for some initial guess, I might reach this solution, right? So we have multiple solutions based on the initial conditions that we choose, right? So for like the previous initial conditions, we got to the 0 0 0 solution. Now if I change the initial conditions, and then I get to some other solution. So which in this case is this value. So it is basically root 3. I think it's root 3. Let's go. Yeah, it's root 3. So root 3, and 1. Okay. We calculate error. Yeah. So the error is 0. Right. Fine. Now, similarly to this problem, we have three solutions. So if I change the initial condition again to something like -1, -1, or we can also check. Um, yeah. So you see, for that we also getting a 0. Okay. Now let us run for this part. So it has run. Let's see what we get. Okay, so this part is still converging to 0 only, these initial conditions. Let us change them. Still to 0. I think for some other initial conditions, we were getting the other solution. Yeah, so this is the other solution. Minus root 3, minus root 3, and 1. Okay, so if I put these this into that NR function, yeah. So you see, so I'm still getting a 0. That means root 3, and 1 is also one of the solution. Okay. Yeah. So this is basically Newton-Raphson. Okay. Now let us see what the next part is. Yeah. So before I go to that, let us also look at the f-solve and f0 functions. So we can try to solve the same equation, this NR equation, using f-solve. Just copy this. Okay, let me just type help first. So this is f-solve. Solves a system of nonlinear equations of several variables. Solves attempts to solve equations for one of the following form. Implements three different algorithms: trust region, and trust region dogleg, trust region, and Levenberg Marquardt. And then we have some options. Okay, so this is the basic syntax. We need to pass a function handle and then initial condition, initial guess, not initial condition. Okay, then it gives us the output, right? So this is a nonlinear problem with which we can see like we have been these independent variables being multiplied together, right? So this is a nonlinear problem. Yeah, since we saw that fsolve does not require the function to return the Jacobian, so I will just remove that part. Okay, let me change that. So I will save this. Right. So now let us run this. So x solve at the rate, and I will give my initial condition as -1, -1, and 0. Okay, so it says that equation solved. Further, there are further more options for the output that we can check for this fsolve. So like we can check my x result output. Then I think there is the residual and the function val. Okay, let me just take the, I don't remember the sequence of this. I think the second one is, yeah. So f val, that is the function value. Then we have exit flag, and then we have the output. So output is basically the number of returns a structure output with the number of iterations taken in output iterations. And it also outputs the Jacobian at that endpoint. So that also, if you want to check, then you can check that. Okay. So we will just take the first two values, so x, f val, and we can check the exit flag. So exit flag basically means that the problem has solved correctly if exit flag is 1. Otherwise, I think it is also mentioned somewhere over here. Yeah. So these are all the values of exit flag that you. So actually, what my advice is that you should always check the exit flag and the residual, which basically f val, because sometimes it shows that equation solved, but it's not an exit flag of 1. Sometimes it's just that the change in residual norm is too small, or change in excess is too small, or compute search difference direction is too small, but it still shows that equation solved. Okay, so that's why you should always check exit val. Then we have a solve function handle. Then sorry, the initial condition. So this time let me give some other initial condition: -4, -4, and 1. Probably this should converge to root 3, -√3, -√3, and 1. So let's see. Okay. So exit flag is 1. That means it's solved the problem correctly. Yeah. So f val is also close to 0. And then the solution that we are getting is -√3, -√3, and 1. Okay. So this is f solve. Similarly, we have f0 also, but f0 is for the single variable. This is basically f solve is for like multi-variable case. F0 is for a single variable. So f0 single variable nonlinear zero finding tries to find a zero of the function near x0 if x0 is a scalar. Okay, so this basically runs this is basically the root what what's that method called? Second method, I think. I think it's the second method. So what you basically do is you try to take 2 points on the function. Suppose this is the function. To you take 2 points on the function. I think it's the midpoint method or second method. I don't remember exactly, but you take the 2 points and then you calculate the function value. If the multiplication of the function values is negative, that means one of the value is positive, the other one is negative. So the solution might be somewhere in between. So then take the midpoint and calculate at that. Uh, if the midpoint is also like the multiplication of this f val at midpoint is also opposite sign, then basically you change this side, this x value to this value, and then you can continue doing so. Okay, so I start with this point and this point, and then this middle point. So I can see that the multiplication of these two vals would be less than 0, then that means the solution is between these 2 points. So I change this point with this point, and now I calculate the midpoint, which would be somewhere over here. So if I calculate now the product of this value and this value, then that is basically positive. That means I don't have any 0 between these 2 points. And similarly, if I calculate product of this value and this value, that means it's negative. That means the 0 is between these 2 points. So I replace this point with this point, and I continue doing so until I get a 0. Okay, so that is basically what f0 is trying to do also, right? Yeah, so yeah, so the function, we also here need to give a function handle and the initial guess. Okay, but since this is like, we cannot solve this function using f0 because it's like multivariable. I think I have a function somewhere. Yeah. So we can try to solve this function, 2 minus x plus log x. So because of this log x, this function is also nonlinear. Okay. So we'll create this function. That's our function handle, and then we just need to pass it to f0. And we need to give the range of initial guesses, right? Between which two regions we want to check, right? So I will give like 0.1, 1, and solve this. Yeah. So we get the solution as 0.158. Okay. If I put that in this function, so if I calculate the function value at solve, so I get a value that is close to 0 only. Okay. Yeah, so we saw fsolve, the use of fsolve and the use of f0. F0 is for nonlinear single variable root finding, and fsolve is nonlinear multivariable root finding. Okay. Right. So let us now. What's the next part? So we have these numerical integration, right? So, so first we will look at I'm not going through numerical differentiation because you guys already know that we have three rules, three different types: central difference, forward difference, and backward difference. We have already done that in. We have pretty much have done that in all the weekly assignments. So I'm not going through them. I will just go through numerical integration. So the first one is trapezoidal rule. This is basically like I have 2 points and I join them. Yeah, so if I take some point, let's take this one only. So I have 2 points. One is this point and one is this point. I on this curve, right? So I want to approximate the area under this curve. So I take 2 points on the curve and I join them using a straight line. Then this is like a straight line parallel to x-axis, y-axis. This is a straight line parallel to y-axis, and this is like a line on x-axis. And then we join these two using a straight line. So we have these two lines as parallel. This is a straight line and this is a straight line. So this is basically the area of the trapezoid with the so we know the two parallel sides, the sum of two parallel sides, that is basically FA and FA plus H. So yeah, like this is the A point and this difference is H. So this is like A plus H point. So this is basically sum of two parallel sides. We multiply that by the distance and then we divide that by 2. So it's like area of the trapezoid, okay? So if A times H will give you the area of this, then if A plus H minus H will give you minus if A plus H minus FA will give you this side. And then this is H. So H times FA minus H, FA plus H minus FA divided by 2 will give you this area. And then when you add those two together, so we have like FA over here and minus FA by H over here. So we get this FA H by 2 in positive. So that is how we get the area this curve of this curve. Okay. We can take like multiple points, closely spaced multiple points. So like if I take 2 points over here, so yeah, this is basically a straight line only. So we can get a better approximation, right? So I take 2 points over here and then this is a straight line, 2 points over here and then this is a straight line. So we can get a pretty good approximation. We just need the points to be closely spaced. Okay. If the points are very far off and there is a lot of nonlinearity between the 2 points, then we get very wrong approximations. Okay. So it's a third order accurate. So if we decrease our h by a factor of uh, 10, then overall or our accuracy decreases increases by a factor of 100. Okay, or error decreases by a factor of sorry, not 100,000. Right. Then there is Simpson's 1/3 rule. So and then there is also a 3/8 rule, which I'm not going through in this one. Yeah, so in 1/3 rule, we basically take 2 points, 1 point in between the two basically given points. So we approximate this using two straight lines. Or if you go through the mathematics of this, so if you look at the mathematics of this, then basically Simpson's 1/3 rule is like a second order approximation to this. But for simplicity, I have just made joined them using two straight lines. Then there is 3/8 rule where we take 2 points in between, right? And then we get a cubic approximation. So it's like between 2 points between like I have 2 points over here, so I can join them using a straight line only. So it's like a first order approximation, not first order, like a linear approximation. Then in Simpson's 1/3 rule, I take I take like 2 points then I can pass a second order or quadratic quadratic equation, quadratic curve through these 3 points. So I get a better, but much better accuracy or much lower error as compared to the trapezoidal's rule. Okay. Yeah, so the formula for Simpson's one-third rule is Fa plus 4 times of Fa plus h, which is this midpoint, and then Fa plus 2h, which is this point. And we take this summation and multiply it by h by 3. Okay. Here our h is b by a by 2, because here h was just this point minus this point. In this case, since we are dividing it into 3, so we divide that, we take h as b minus a divided by 2, so that we get 1 point in between. Okay. It's the order of accuracy is order h5, so the error is much lower as compared to the trapezoidal rule. Fine. So let us look at simple example. Take much time. Mm, Okay, I think I don't have the example for that. Let me just fetch the example from previous classes. B5. Or else what we can do is we can, let us leave that. We can simply try to solve the problem that I have selected over here. Yeah. So we can try to find the body or area, volume of the body connecting these 3 points. Connecting not these 3 points, these 7 points. So yeah, basically if I do this, then at x is equal to 0, d is 5, then 5.5, then 6, then 6.75, then 6.25, 5.5, and 4. So we have a surface like this, and we are rotating this around this x-axis. Okay, so we want to calculate the volume of this revolution. Okay. Fine. So h, we can see that h is if I'm using trapezoidal rule, then we can see that h would be, let me just create a new script. Then my h would be for, let me, trapezoidal rule. So my h, my x is 0, 2.5, 5.0. And then we have d as yeah, so that is our data. So now h would be in this case just 2.5, because yeah, let us just take that as like this d as first point, this as second point. A much better way would be that we can sort of, yeah, we'll do that using Simpson 2 3 1 8 1/3 rule also. But so right now what is happening is that using trapezoidal rule, we are approximating this as a straight lines between these 2 points. Okay, and then using that we are calculating the volume. Okay. Yeah. So the formula is Fa plus H by 2, and then we continue doing that. Okay. So yeah, one more thing. That will just give us the like a cylinder, right? So what we do in cylinder, pi r square h. So we calculate the area of this circle, and then we take that h times to get the volume of the cylinder. The other thing that we can do is like this is basically r, this is h. So we get something like the area of a uh, small strip, right? So this area of this small strip would be uh, 2 pi r, and then 2 pi r x, like is it 2 pi r? Mm, how do we do this? Pi r is by 2 pi r dr. No, yeah, that would eventually, like, it's not that, because that would be like I'm taking a uh, element like this, and then I'm calculating the area, and then I'm doing, so that will basically a double integral if I do that. So there should be a dr over here, and then a dx, and then I take two integrations, right? So what we do in cylinder is basically we calculate the area of a circle, pi r square, and it takes h, right? So similarly in this case we calculate the area of this small circle, uh, and then we calculate the area of this small circle, and we just multiply that. Okay, fine. The other thing that we can do is yeah. So solid of revolution diameter d, estimate the volume of the solid. Yeah, so we calculate the area of in each of these circles, and then we basically use trapezoidal rule to linearly make these, like from this circle to this circle, join them using a linear line, then linear line, and then we calculate the volume. Okay, so that would be basically, yeah. So if I go by this formula, this is like for 2 points. If I add multiple points, then if I add like one more point over here, then if I do that, add that to this, then this a plus h would become twice, and then I will have a b point, and like that it will go. So all those, so it's like the end points are only calculated once, and all the midpoints are calculated twice. Okay, so that is what we'll do over here. So we using trapezoidal rule, h by 2 multiplied, sorry, h by 2 multiplied by not a, we will multiply that by sorry, the first one a1, then twice a from 2 to end minus 1 plus a end. Okay, fine. Similarly, we can do with the Simpson's one-third rule. So whereas in trapezoidal we were approximating each of these like area between the cubes using a straight line, in two-third rule we will be using a quadratic term, right? So that will give us a much better much better approximation. Okay. Yeah, so if I do this, replace this with Simpson's one-third rule. So if I add one more point over here, so basically for multi-dimension, what will happen is I add one more point over here like this. Right. So I have one point, I have one point here, and I have one point here. Okay. So this is a plus h, a plus 2h. Then this would be a plus 3h. So this will again add up like 4 times. And this is a plus 3, 4h, right? So that will again add up over here, right? So all of these terms, all of the even terms, not even, all of the odd terms in h, like a plus n plus 1, a plus n plus 1 h, right? All the odd terms, they will add up 4 times, and all the even terms will add up twice, right? And the first initial point and end point would be 1 times. Okay. Yeah. So we sim by 3 multiplied by so the first odd term over here would be like the based on the indexing would be the event term, right? So this will be multiplied by 4. So that would be like from the second in increments of 2 and up to end minus 1. Okay. Right. And then twice uh, third element onwards in increments of 2 and minus so that is like a plus h, so and minus 2. No, this should be n minus 1, this should be n minus 2, and one more thing, this should not be a square bracket, and then plus twice, and then the last term, right? Okay. So now let us check this. Okay, yeah. So R is a vector. So this power should be element wise operation, right? Uh, why am I getting a scalar vector over here? Why am I getting this? Mm, okay, sorry, yeah. So this should be like sum. That is a vector that we are extracting over here. Similarly, this should be sum. And similarly, so this is what we are getting using that, using trapezoidal rule, and this is what we are getting using the Simpson's rule. We have the inbuilt trapezoidal function also. So let's just check that. So we just need to pass on all the y values and it will just calculate and give us the area. Now this like uses a unit spacing. So we need to multiply with our own h. So like RH is not 1, RH is 2.5. So we need to multiply with that. The other way is that we can simply pass on both x and y values. That way we don't need to multiply it with RH. It takes care of that automatically. Okay, so since we have both uh, x and y values, so I will just do that. Okay, so inbuilt trapezoidal rule. Yeah, so the function name is trap z x a. So we are getting the same solution using both. Why is Simpson solution so off? I think we doing some error over here. It should not be off by this much, this large value. Uh, what is the error that is there? 2 times for the elements. Okay, yeah, this should not be 3. My mistake. Yeah, so now it's closer to the trapezoidal solution. Okay, I was doing increments of 3. That was the error. Fine. So that is there. Now there is another quad function inbuilt that uses basically Gauss quadrature to calculate the volume. Not volume, to calculate the area. Uh, You can look at this if you want. Basically, Simpson's quadrature, numerically evaluate integral using adaptive Simpson's quadrature. So adaptive, basically adaptive means how we vary this h value. So in trapezoidal rule, this h is constant, whatever the value we give. Even in inbuilt MATLAB function trap z, the h value is constant. So what value, based on the distance between the two x values, it gets that h value. In adaptive quadrature, we change this h value adaptively using based on some error tolerances. Okay, so you can go through the documentation and look into more details on this part. Yeah, so that is there. Now let us go to the next part. We saw this example. Now we have the OD, like Runge-Kutta, Euler's method, like OD solution. So until now we were doing integration of basic simple function, not even, yeah, we were doing integrals of basic functions, right? Now we will be doing solutions of ordinary differential equations, right? So first one is Euler's method. There are two parts: Euler's explicit method, Euler's implicit method. Then we have Runge-Kutta methods, and then we have the MATLAB inbuilt solver ODE45. Okay, so Euler's method. I will again go to my tab. Yeah, so we have Euler's method. Um, there are two parts in it: explicit, then implicit. Similarly, in Runge-Kutta methods, we have like RK2, RK3, RK4, and like that. Then we have OD45. So explicit, implicit, there is a very subtle difference. Uh, so yeah, let us say that the function is y prime is equal to f of x. So this y prime we can discretize at like yi plus 1 minus yi divided by, if it's a function of x, so delta x is equal to f of x, right? So yi plus 1 would mean, would not would mean, would become yi plus delta x f of x. And we can solve this like incrementally from given like x is equal to 0 to some boundary like x is equal to a to some boundary condition b. We solve this incrementally and we get the value of the function y, okay, as a vector. In here, this xi that we are using this from the previous time step only, okay. This is simple, there is no problem. And now let us look at other one. So m is equal to f of x comma y both, okay. So now still the explicit method, the solution remains the same: yi plus delta x f of xi yi, okay. So this yi and this yi, they are both from the previous time step, okay. If I try to do so, that this means basically explicit, because we are the current the current yi plus 1 only depends on the previous stages, previous values x, and previous stages value y values, okay. In implicit method, we basically write this as, so this Now here this fx f function. Here f function, the inputs to this f is xi plus 1 and f yi plus 1. So the current value of yi plus 1 depends on yi plus 1. These two values are like interlinked together. It's not a simple process where we calculate yi, then y1, then calculate y2, and then calculate y3. Here, this for calculation of y1, 2, 3, for calculation of y3, uh, we need the previous y2 also, but this calculation of fx, we also need y3 itself. So it's like a circular dependence. Okay. So for this, like we cannot solve this using these sort of incremental methods. What we usually do is we formulate this as a nonlinear problem, like root finding sort of problem, and we try to solve this. Uh, yeah, so if we take this entire thing to that side, then it becomes yi plus 1 minus yi minus delta x yi plus 1 is equal to 0. Okay. Now this should be like if this solution is satisfied, then this should become 0. Okay. So that is basically our uh, input to some nonlinear solver, root finding solver. Okay. We uh, we try to solve for yi plus 1 using this equation, and we continue doing so from x is equal to a to b. Okay. Now what is the benefit of this? The benefit of this is that since let us first look at the drawback of explicit solver. So like since this is incremental, right? So if there is some error in calculation of yi, then that error adds up in the calculation of yi plus 1, and then eventually it adds up in even more in yi plus 2, and like that it sort of builds up, the error builds up. So the solution might become unstable after a very long after very long interval, right? This does not happen in implicit methods, because the current yi is the current fx, like the current function f is dependent on itself. So it it makes the solution, it does not make the solution go unbounded. It always bounds the solution. We are solving a root finding problem, so that bounds it, does not let the overall integration go haywire. Okay. But there is a drawback also, because since we for each of these steps we need to do a root finding. We need to do root finding to calculate each yi plus 1, right? So this also takes time. So that is why implicit methods are slower as compared to explicit methods. In explicit methods, we just there is a simple multiplication and addition. So when do we do this incrementally? There, due to this circular dependence and this root finding, the solution is usually takes longer, but also it's much more stable as compared to explicit methods. Okay. Yeah. Then we have Runge-Kutta methods. So basically in Runge-Kutta methods, we do yi plus 1 is equal to yi plus w1 fx x1 y1 w2 fx2 y2, like this, right? And then how we choose this x1 y1 and this w1 w2, that depends on the family of Runge-Kutta method. So if it's a RK2 method, then I think yeah, you can go through the lectures. If it's an RK2 method, then this becomes h by 2, and then it's fx1 y1 plus f of x1 and y x plus h, and then y plus h times this fx plus 1, like that. You can go through the previous lecture notes. Okay. What we are interested in is in RK4, which is the most widely used solver, and OD45 also uses a variation of RK4 method with some adaptive time stepping. So that's why this 4 5. So RK4, the step is we get this h by 6, and then we have f of xi yi plus f of xi plus h by 2 y plus h times of f of x1 y1 by 2, and then of x plus h by 2 y plus h by 2, and f of like this term over here, and then last we get x plus h, and then y plus h times this whole term over here. Okay. Yeah. So we will look at these in MATLAB, how to do this. Yeah. So let us first look at the Euler's explicit and implicit method. So first we will look at Euler's explicit method. So I have the problem over here. No, I don't have problems over here. Fine. Yeah, so we will try to solve this y prime y dy by dt is equal to minus 2ty using Euler's explicit method. We are initializing with like at t is equal to 0, y is equal to 1. Okay. So given to us, these are like the initial conditions. We want time to go till 5 seconds. H value is 0.2, so we are taking in increments of 0.1. So the number of times we need to run the loop is like Tn minus T0 divided by H. Okay. This is our initialization of the time vector. So T0 is 0 and Tn 5, and in increments of 0.1. This is the vector of y. Okay. And then this is a initial y value, and yeah, so this is the function like f of x comma y, or f of t comma y in this case, and we multiply this f with h and we add it to y. So this is just like incremental calculations that we are doing, consecutive successive calculations that we are doing. This is the true solution, and we will plot both true and absolute solutions over one another. Okay. Yeah. Also note that this loop goes from I is equal to 1, like so yi we have already calculated, like the initial condition that is given to us. So this goes from 1 to n. So we start our calculation from y2. Okay. Now let us run this. Yeah. Okay. So the true value is the green one, and the calculated value is the red one. Okay. So we can see that it's still a pretty good pretty good approximation. Okay. Now let us do first, let me increase this h value to 0.5. Then, so you can see that we are starting to get still the solution is bounded. It has not gone unbounded, but the solution that we are getting is bad as compared to the true solution. Now let me increase h even more. Yeah, so now you see after a certain time the solution goes unbounded. So that is the problem with with these explicit methods. Initially, yeah, this error, the error sort of goes on adding up together. So for y1, the error is less, then y2 the error becomes more, then y3 it again becomes much more, then y4 it becomes even more, and eventually for y5 it goes like unbounded. Okay. On the other hand, if I decrease h, then we get much better approximations. Yeah. So now you see both the green and red one, they are sort of superimposing on one another. So that is the explicit method. It's simple, but we need to check the values of the increments that we are doing, the discretization that we are doing. Otherwise, it might become unbounded. Now, same problem using Euler's explicit method. So the initialization remains the same. Okay, let me just make this 5-second. 0.5, 0.1. This is the initialization, same. Yeah. So now here, I'm calculating my time, which is basically the time at the previous time step plus h. So this t is the time for the current time step. And then I write that equation y minus h times, this is basically my fx, f t comma y, and then this is like y. This is my y from the previous time step. Okay. This is the y for the current time step that I need to find, and you will notice that this is the same y that is over here. So this function is basically this function is basically a function of the y value at the next time step, yi plus 1. Okay. So I will initialize my I will give an initial guess of the current yi, because we know that since we are even if we are taking a very large h value, we know that the next solution to this differential equation will not deviate much from the current solution. It will just increment on the current solution with a slight amount. Okay. So I will give the current solution as my estimate. Okay. Then once it solves this, then my ti plus 1 becomes my t value, and my yi plus 1 becomes my y, and then the step again continues. Okay. Yeah, and then I am plotting again over here. So I will run this. It might take a long time. Let's see. Yeah. So for 0.1, this is what I'm getting. If I do the same 0.1 for the explicit case, okay, I think I need to create another plot, another figure, not plot. So I will do this on figure 2, and I will do this plotting on figure 1. Yeah, so this is my implicit method for 0.1, and this is my explicit method for 0.1. So you can see that for the same h value, my implicit method is much better as compared to my explicit method. There is a large gap over here, then a large gap over here as compared to this one. Okay. Yeah, but the real, so let me do 0.5. As you can see, for 0.5 over here, I was getting a very very crude approximation, right? Yeah. So 0.5 for explicit, it was giving me a very crude solution, but this is also a crude solution, but it's acceptable compared to this, right? Now, if we make h is equal to 1, so it's a good approximation. In 1 for this, I think it was becoming unbounded. Yeah, so for 1, this becomes unbounded, but it's still giving me a good approximation. Similarly, if I make this 5, it will still give me a pretty good approximation. Okay, fine. So that is the Euler's implicit explicit method. Now we have RK4. So let us solve the same problem using RK4. This is just my initialization. So I will initialize this to 0.1 only. This is my function handle. Uh, this is I'm initializing all the required vectors. Then this is the solution for RK4. Okay. So for I is equal to 1 to n, I calculate these the 4 k values, k1, k2, k3, k4, and then I calculate finally my yi. Okay, and then the step repeats. So it's basically very simple. The first one is for t comma y at the current time step. Then I increment that t with the small h by 2 amount, and I increment my y with whatever value I'm getting, whatever the function value I'm getting for for t comma y. I take that same function value, I multiply it by the h, and I add that to the previous y value. Okay. Then I get my k2. Then the same thing I'll do with my k3. So instead of k1, I use my k2 over here, and then I calculate, and then I do the same with k4 for calculation of k4. Okay. And then we add this all together to get the y value at I plus 1 time step. Then this is just the plotting part. So I will do this. So you can see even for oh, okay. Yeah. So both of these solutions are superimposing on one another. So like RK4 is very good in solving these ODE problems. Like we can see that we cannot even find difference between the values. Also, if we check at the error, yeah, so you can see that the error is very small. It's on order 10 to the power minus 5. Okay. Even if I use a not large, 0.5. Yeah. So after certain time, this RK4 method, the explicit RK4 method, this also mm, becomes unbounded, right? So we need to check for that also. It's not becoming unbounded. Yeah. For this, it's fine. Okay. Yeah. Now we can try to do the same thing using ODE45. So I already have a function for ODE45. The same thing. So we are using a tolerances of 10 to the power minus 1 for now. Let us increase that 0.6, 0.6. So this is the function handle. We need to pass a function handle to OD45. This is the time steps that we want the solutions to. So this is not the time steps internally at which OD45 calculates the solution. It uses an adaptive time stepping, so it does it goes back and forth. It's not a linear sort of thing as in RK4. It goes back and forth. It changes the value of h and all those things. But the output wise sol and t sol values that it only gives us on these in on or for these intervals only. Okay. This is the initial conditions, and then we have these options that we pass on to this. Yeah. So now let's do this. Yeah. So you can see that sort of superimposing on one another. Now let us decrease this tolerance, but still, because since this is an adaptive time stepping, so we assume that the solution would be good only. Okay. For some problems, you might need to check these tolerances, because for some very low tolerances, also the OD45 will give you a warning that it cannot meet the integration tolerances. And for very high tolerances, the errors that you are getting might be very large and not good enough for the work that you are doing. Okay. Fine. So that is the ODE solvers, and then we have the integration. So we have these stiff ODEs where we need to use the OD15s. The problem remains the same. The syntax remains the same. Instead of OD45, we just need to write OD15s. Okay. So it will solve it using the stiff OD15s solver. So step OD is basically where the suppose you have like two variables, two dependent variables. So one of the variables is uh, what is it? It's like the time scale for one of the variable is very high, very large compared to the time scale for the other variable, right? So yeah. So stiffness occurs when the some components of the solution decay very more rapidly than others, or when if it's a linear coefficient system, then stiff if the eigenvalues have negative real part and the stiffness ratio is large. So like if I sort of write this as x dot is equal to ax, so I calculate all the eigenvalues of my A matrix. So if the ratio of those eigenvalues is very large, then the system is stiff. So all of these three basically means the same thing. If the ratio of to a negative real part to negative eigenvalues is very large, then basically that means that one of the time series is decaying very rapidly as compared to the other. Right? Yeah. For that you need to use OD15s, because that it takes care of the uh, time stepping, like internally it takes care of the step length for the solution. So OD45 might give you the same performance for step ODs also, but it will take long time, and it will take a lot of internal time steps to do that. OD15 is takes care of everything. So if one of the time series require very subtle time stepping, very small time stepping, it will do that. And then for the other one, it will again start to take very large time steps, so that the solution converges quickly, right? So all that thing you will just go through the solution. You can just go through the documentation. It's simple. But for the purpose of this course, you just need to like check if it's a linear constant coefficient system, then just check the eigenvalues, and if the ratio of eigenvalues is too large, then just choose your OD15s. Otherwise, you can sort of just integrate it using OD45, and then if you see that one of the time series is decaying very fast as compared to the other one, then switch to OD15s. Fine. So yeah, that is the stiff ODs and non-stiff ODs. Right. So I think I have already touched the 2 hour mark. I had some other problems, but I have already discussed these problems in my previous classes, so you can just go through that. Then there is a regression and interpolation, which is also very simple. You guys can go through them. Yeah. So that's all from my end. See you on Monday for the interactive session for week 12. Thank you.